Jai Hind students, in this lecture we will study functional dependencies. These are the contents of the topic. Functional dependencies, its basic definition, types of functional dependencies, how to calculate the attribute closure through functional dependencies, Armstrong's axioms, equivalence of functional dependencies, and canonical cover, that is the irreducible set of functional dependencies. So, in this lecture we will study these contents. Right? Now, if we start with the basic definition of the functional dependency, we can represent A tends to B. It means B can be functionally determined from A. What do you mean by that? If we have the value of A with us, we can functionally determine B, right? We can take an example of student, right? So, if we have student number, we all know that if we have student number, we can find out each and every detail of the student in the database. Let's suppose we are having a table student in which we are keeping all the records of the student. Let's suppose roll number, section, name, personal record, section, marks and other informations, right? So, if we have the roll number, we can find out the name. So, we can say that function dependency roll number tends to student name exists. You all check your result on university site. Once you give the roll number, you can able to find out your marks of that particular semester or whole semester marks, right? So, that student number is basically what? We can say that the student number is basically determinant in that case, right? And the other information of the student like name, like his marks, all are dependent. So, if we are representing x tends to y, or we can say A tends to B, it means this y or this B is what? Dependent, and this x and A, it is determinant. If we have that x or A with us, then we will be able to determine that y or B, right? Okay. So, this is the full definition of the function dependency we will study. Just a minute, right? Okay. So, here we can see a small relation R with two attributes A and B. We are having some values of A and B. Here we can see these are the subjects and these are the codes for those subjects, right? So, we can see that A is the subset of that relation R and B is also the subset of the relation R. And if this function dependency hold, it means A tends to B. It means what? If we are having the value of A, we can determine the value of B, right? So, if we know the subject code, we can determine the subject name. Okay. So, what is the full definition of the function dependency? If a tuple value on A is something, then the tuple value on A should be the same for the another tuple. If somewhere we have written this 101 code, it means what? Only the value of computer network can be determined. Anywhere we found the value 101, it can only determine the subject is computer network. If we found any value 103 as a subject code, so it will determine DA is the subject name, right? So, if T1 on A is equal to T2 on that A, right, then it must be T2B, T2B is equal to sorry, this is the T1B is equal to T2B, right. So, if we know this A, we can determine B on the basis of A. Okay. Now, the types of functional dependency. Let's suppose we have given this A tends to B. Okay. So, the first type of functional dependency is the trivial. We can have all the, okay. So what do you mean by trivial? If B is the subset of A, then if we are saying that AB tends to B, what we are saying here, that B is the subset of this. Okay, here we can see that if the functional dependency extends to Y whole, where Y is the subset of X, then it is called the trivial. Here we can see this B is the subset of AB. It means what? It is trivial functional dependency. It is valid, but it is not informative. Why not informative? Because we are not deducing any of the new information here. Whereas, when we can see this non-trivial dependency, what do you mean by non-trivial functional dependency? If functional dependency extends to Y whole, where Y is not the subset of X, then it is called non-trivial functional dependency. Here we can see that AB tends to ABC. So it is valid functional dependency, and we are finding a new attribute here. Through AB, we can find out ABC, right? So we are finding out a new information here. So it is valid, and we are getting some new information. So it is known as non-trivial functional dependency. What are the trivials? When we are not getting any new information. So these functional dependencies are valid, but we are not getting any new information, right? So these are the two sets of the functional dependency. These are the two types of the functional dependency, right? So if we can, if we want to practice, we can have a simple example. Okay, so here we can see that if we are talking about this functional dependency, let's check in the relation what values on A, the value of BC can be find out, right? So here we can see the value of A is Z, and the value of BC can be find out 2, 3. So if this functional dependency hold, it means what? For every tuple, if we are finding out the value of A is Z, it means the value of BC should be 2, 3 if this functional dependency holds, right? So we will check here in this relation. Here we are finding out Z, here we are finding out Z. So Z is 3 at the 3 places. So for this Z, the value of BC should be 2, 3. Yes, it is 2, 3. This is Z, so value of BC should be 2, 3 again. Yes, it is there. Value of Z and value of BC is 2, 3 again. It means what? For every tuple T1, value of A is equal to tuple T2 value of A. So these two tuples are same for the value of A. Then these two tuples are same for the value of B, right? This is what the definition of the functional dependency we have studied in that slide. So we can find out that. So yes, on the same value of A, we can find the same value of BC, correct? So this functional dependency hold on this relation. Let's check this C tends to DC, DE. So this functional dependency hold or not, right? So we can check for this first tuple, value of C is this 3 and DC is 4, 5. So for this 3, we should get the 4, 5 in each and every tuple. So here we can find out this C 3. Here we are finding out the 4, 5. Yes, here we are getting this 3, but here we are finding out some different value. Here this is 3, but we are finding out some different value. So on same value of C, we are getting the different value of DC. So this functional dependency not hold on this relation. So this first functional dependency hold on the relation, but it is not holding, right? So this is how we can check the functional dependency is holding or not. Now, attribute closure or closure set of the functional dependency, right? So whenever we talk about the attribute closure, we can find out the attribute closure on some set of functional dependency with the help of functional dependency, right? So attribute closure is nothing but the closure set of attribute that can be defined as a set of attributes which can be functionally determined from it. So attribute closure means what? If we are finding out the closure of A, we will write if A is the attribute and we are finding out the closure of A, we will write A plus, right? So we will write the attribute closure means every attribute which can be find out from this A. If we are having A, how many other attributes we can be able to find out? That is what the attribute closure, right? So here we can see this R1 is the relation with A, B, C, 3 attributes are given, and the functional dependency given here, A tends to B and B tends to C, right? Now we need to find out the attribute closure A. So we will start with A, because A we have already with us, and if we have A, what we can determine? Through this functional dependency, we can see if we are having A, we can determine B. So we can write AB. If we are having A, we can determine B. So we are having AB in our hand, right? Through this function dependency, we can find out that if we are having B, we can determine C, right? So we have A and B. It means what? We can determine C also through this function dependency. So now we are having ABC. It means closure of A is ABC. That is the whole relation. It will become the key. If we are getting attribute closure that covers all the attribute of that particular relation, it means that particular attribute can become the key of that particular relation. So here key is what? A, right? So these function dependency set can be used to find out the key of the relation. Candidate key can be find out through the attribute closure set, or super key can be find out through the attribute closure set by the same steps. Okay, take one another example. If we are having a relation R2 with attributes A, B, C, D, E, F. Now here we have given the functional dependencies set like this. Now we need to find out the closure of D. So we'll start with the first step. What we are in our hand? We are having D in our hand. So if we have D, what other attribute can be determined? We can see if we are having D, we can determine through this function dependency. If we are having D, we can determine A and F. So here we can see we are having D already, and we can determine A and F. So we are having in our hand A, D and F. Okay. Now if we are having A, D and F, what other we can determine? If we are having A, we can determine B. So now we are having A, B, D, F in our hand. If we are having A, B, D, F in our hand, what other thing we can determine? No, we cannot determine anything from this functional dependency. No, we cannot determine anything from this functional dependency. No. So nothing can be more determined from this A, B, D, F in our hand. So the attribute closure for this D attribute, so attribute closure of this D attribute is A, B, D, F. This much attribute can be determined if we are having D, right? Let's suppose we want to determine D and E closure. It means the combination of D and E closure, right? So what we are having in our hand? We are having in our hand D, E. D and E we already know, right? So if we know D and E, what other can be determined? If we know this D, A and F can be determined. If we know this E, C and F can be determined. So what we will now have in our hand A, D, E, F. Okay. So if we have A, D, E, F in our hand, what other thing we can determine? So here we can see that E, okay, C, F we can determine, and if we are having A, B can determine. So at last A, D, E, F we are having, and B can be determined, C can be determined. So at last we can have A, B, C, D, E, F. So whole relation can be determined from this closure of D and E set, right? So what we can say to this? It can be the super key. It can be the super key of this relation, because we are able to determine each and every attribute of this relation, right? So if we know about the functional dependency, we know about the set of functional dependency types and all, and we follow these steps to determine the attribute closure, we can determine the super keys and candidate keys of the functional dependency, right? Okay. Next, very important rules are Armstrong axioms and Armstrong rules, right? So these are the primary rules, three primary rules Armstrong has given, and these these rules are the secondary rules which can be inferred from the primary rules, right? So we will not have the proof of these, we just use these rules, we will study these rules and use these rules in our for the calculations, right? So if we talk about the primary or basic inference rule, first rule is the reflexive. Reflexive means what? If y is the subset of x, then we can write that x tends to y. Y is the subset of x, right? So it is what the trivial functional dependency which we have studied in the previous slide. Augmentation is one another rule. If x tends to y hold, then we can augment the same value at the both side of the function dependency, right side and the left side both. Okay, so what we will write then? If let's suppose we augment z on the both side, then our function dependency x tends to y will become x z tends to yz. Okay, so we can simply augment the same value at the both side of the functional dependency. The next rule is the transitivity. If x tends to y holds and at the same time y tends to z hold, then we can say that x tends to z hold, because z can be determined by y and y can be determined by z. So we can say that z can be determined by x. So this is what the transitivity. So these three rules are the primary or basic inference rules of Armstrong, and these rules are the secondary inference rules which can be derived from the primary rules. Okay. So union rule. What union rule says that if x tends to y holds and x tends to z holds, then we can combine the right hand side. Okay. So we can say that x tends to y, z holds. This is what the union. We are combining the two functional dependency here. Next rule is the decomposition. If x tends to yz, then we can decompose these two function dependency. We can see these two function dependency here, x tends to y and x tends to z. So we are decomposing. So this is just opposite to the union, or we can say that the opposite is just union is just opposite to the decomposition, right? Next rule is the pseudo transitivity. It means what? If function dependency x tends to y hold and wy tends to z hold, then we can say that yx tends to z, because this y can be functional determined by x. So if we are having x, it's same as having y, right? So we can write, instead of y we can write x here. So this is what the pseudo transitivity. So these inference rule we will use to find out the minimal cover of the functional dependency, right? Next rule is the composition. If x tends to y hold and z tends to w hold, we can combine, right? So we can write what? X z tends to y w. This is what the composition of two functional dependencies we are combining, right? So these are some rules of the Armstrong, and we will use these rules to find out the minimal cover which is required. Okay. So before that, we'll have some practice on these closures of the attribute set, right? So for this example, we can have some practice. We need to find out that AC plus. So what we have in our hand, we are having AC in our hand, right? If we are having AC in our hand, what other thing we can determine? We can determine B from this function dependency. Yes. So now what we are having in our hand? A, B, C. If we are having BC in our hand, we can determine DE. So what is this? AC plus. What is this AC plus? A, B, C, D, E. After that, we are not able to determine this G here. okay, because we are not having the G in our hand, or to determine this G, we should know the G. This is what the trivial one, okay. Here also we can see that find B plus, it means what we are having in our hand, B is in our hand. If we are having B, we can determine D, okay. So B and D, just nothing else can be determined. Here if we are having AB, we can determine C. So ABC, we can determine A and D, we can determine E, but we cannot determine this F, right. Here we need to check B, C, D plus is H or not. So what we are having in our hand, B, C, D. What we other thing we can determine from here, C, D, say E, we can determine this. C already having, okay. What we can determine other, B, C, D, C, D, E, B, C, D, E, and E, C, D, A, B. We are able to determine this. Oh, okay. We are having this B, C. We can determine this A. So A, B, C, D, E, and this. No. If we are having this D, we can determine this A, E, H. So A, B, C, D, E, and H. So this is valid, है ना? We can determine this H through this, right? So this is valid. Now find AG plus. So what we are in our hand, AG. If we have A, then we can determine B. If we are having this, we can determine C. If we are having CD, we can determine H. If we are having CG, we can determine I. If we are having B, we can determine H. It's already in our hand. So we can determine each and everything here, right? So what is the solution here? Yes, we have find out this, we have find out this, we have find out this. Yes, it is valid. We have find out this. Okay, so what is remaining here? Okay, no functional dependency here with this D, so we are not able to determine this D, right? So through functional dependencies, we can find out these closures, right? So these are the example how to find out the closures. Now the next important thing, equivalence of functional dependency. How we will calculate the equivalence of the functional dependency with the set of these functional dependencies, right? So what is the procedure for that? Okay, we are given the two functional dependency sets. Now we need to find out the equivalence of both. So what will be the process? For functional dependency set, FD1 will take the right hand side and calculate the closure A plus, AC plus, E plus, right? Now this closure will not be find out with the functional dependency D1, FD1. We will find out these closure through this functional dependency set of FD2, and then we'll check what we are finding out, right? So okay, so here A plus, if we are having A, we can find out CD. It means the closure is this on the basis of functional dependency this. Closure of AC, what we will find out? ACD. We will find out on the basis of functional dependency too. Closure of E on the basis of this. If we are having E, we will find out AH. If we are having A, we will be able to find out D, C and D. So what we will have in our hand, this one. Now similarly, we'll find out the closure of A and E of these functional dependent from the functional dependency set of FD1, right? And closure of A, If we are having A, we can find out C. If we are having AC, we can find out D. So what we are able to find out? ACD. Closure of E on the basis of function dependency FD1. Okay. So what we will able to find out? If we are having E, we will be able to find out AD. H. If we are able to find out A, we have A, then we will have C and D. So we will find out these. And we can see here FD1 is the subset of FD2, and here we will be able to find out that FD2 is the subset of FD2. So these function dependencies are what? Same. So equivalent, right? Here we are finding out these sets, here we are finding out these sets. So both are the subset of each other. So we can say that these functional dependencies are equal. Let's take another example where these functional dependencies are equal or not. We need to check that. Here we can find out closure of P, Q and R on the basis of Y set, and here we are finding out the closure of P and R on the basis of X. So what we are finding out? P plus is this. Q closure will not be find out from here because here is not a single functional dependency that any of the attribute can be determined from Q, not a single one. So we are not able to determine anything from Q. This is okay. P plus R. So we can see here Y is the subset of X. Yes. But here what we are finding out, X is not the subset of Y, because from functional dependency set X we will be able to find out Q plus different. Here on the basis of Y we are finding out Q plus Q only, but on the basis of functional dependency this set X, what we will be able to find out? Q is already having, R we can reduce from this, right? And we are having R, thus we can find out S also. So this Q plus, if we calculate from the function dependency set X, it is different. Or if we are finding out on the basis of Y, it is different. So what we can reduce, X is not the subset of Y. So function dependency sets are not equal. So this is very important property of this function dependency. So now you will be able to find out the equivalence of function dependency set. The next very important concept is canonical cover. What is this canonical cover? It is the irreducible set of functional dependency. We have given the set of functional dependency where we can find out there are many functional dependency which can be just ignored because that can be deduced from some other functional dependency. We can infer from the other, right? For example, X tends to C is redundant. If we write X tends to A tends to C, it is redundant because here from these two functional dependency we can deduce this. So we need not to write this explicitly. Okay. Now this functional dependency set is given to us. Can it be simplified? Let's check for the extra attribute or extra functional dependency, right? So here we can see that A tends to B, okay, B tends to C, okay. So here we can find out the C or D. One can be eliminated. So what we can find out, if we have A, we can reduce this C. A tends to B, B tends to C. It means what we can reduce? A tends to C. If we know A, we can determine the C. So this C is basically extra attribute here. This can be eliminated. So how it can be simplified? A tends to B, B tends to C, A tends to D. That C was extra element, we can remove that. Here also we can check for the extra element. So here we can see there are two elements. What can be extra? Let's check for it. It can be simplified or not. So here we are having these two functional dependencies, so we can deduce A tends to C, which is not written here because it is redundant. But if we know A, we can deduce this C, so no need to write this C. So what we can do, we can eliminate it. So what we can write, A tends to do instead of AC tends to D. C can be deduced by A, so we need not to write it. So it can be simplified like this. So these are the simple example of the how we can get the irreducible set of functional dependency, how we can remove the extra elements or extra attributes from the functional dependencies. We can take an example, full example of that. Here we can find out anything extra in these two functional dependency. Yes, we can find out this B is extra here. Okay. So what we can see, why this B is extra here? Because this C can be determined from A. We are writing C can be determined from A. So this B is extra here because C can be determined only from A. Why require B? Remove that. Okay. So we are removing this. Here, let's check what can be removed here. So here nothing is can be removed. Here we can check something can be removed. So what we are saying, C is extra here. Why we are saying that C is extra here? Because functional dependency X tends to C says that C can be determined from A. Right, C can be determined from A. So if we are writing here AB tends to C, the C can be determined from A. So this is extra. Why need to write? Because it is written here already. So we can infer that AB tends to C will be sufficient. We need not to write this. C is extra. Oh, I'm sorry. We need to write this. We are eliminating this C. C is extra. So we are writing this AB tends to D. It's my mistake. Now take a full example of the canonical cover. Let's suppose we are given this relation ABC. Given this relation on 3 attributes. These are the functional dependency sets. So we can find out the canonical cover or minimal functional dependency set. So how many functional dependency or can be removed or some extra elements can be removed, we can check for that. So here what we can see, we can see that we can combine A tends to BC and AB, A tends to B into this, right. So set is now this. Now here we can find out the A is extra in AB tends to C. Why this A is extra? Because B tends to C is already written. We can determine C from B only. So why is that A required? So this can be removed. Yes. So now we are having this functional dependency set. Now we can find out C is extra in A tends to BC. Why the C is extra in this? Because we'll check if A tends to C is logically implied. Why? A tends to B, right? So due to transitivity, we can write this. So this is sufficient. We need not to write this, right? So at last, what we have, the canonical cover, A tends to B and B tends to C. This is the irreducible set of functional dependency. Further, we cannot reduce, right? So till this, we can reduce. So for these functional dependency set, minimal cover is this, A tends to B and B tends to C. So that is how we can calculate the minimal cover. In the next lecture, we'll study more on functional dependency. Thank you.